Formal charge can be thought of as the charge that an atom would have in a molecule if the electrons were shared perfectly evenly between the two atoms in a bond. So let's look at some simple molecules, and many of you already know an algorithmic method of calculating formal charge for molecules, and this is similar, but it's a little bit more visual. So it requires first drawing the Lewis structure. So let's do carbon dioxide first. So we take the carbon dioxide and we draw the Lewis structure. And this method will only work if you draw in all the lone pairs. So you've got to make sure that you draw all the lone pairs in every atom that has a lone pair. Great, so there's our carbon dioxide. And what you do is, as soon as you've drawn the molecule, you circle each atom, and when you circle the atom, you make sure to split every bond right down the middle. And this is sort of indicative of what formal charge is doing, right? We're saying that it's the charge the atom would have if the atoms were shared equally between, if the electrons were shared equally between the two atoms. So we split every bond down the middle. And then what we do is we take each atom and we say, okay, how many valence electrons has an atom normally? So for instance, for oxygen, we know it has 6 outer shell electrons, so we'll write 6. And then we subtract all the electrons that are in the circle. So if we look at this circle, we can see that we have 6 electrons. So we've got one there, that's 2, 3, 4. And then we have each of these bonds is 2 electrons, and so we've got 2 electrons in the top bond, 2 electrons in the bottom bond. And so we can say that since we're splitting the bond 50-50, we know that each of those bonds is going to contribute 1 electron into this circle. So there's 6 total electrons in the circle. And so we can now say that there are 6 electrons in there. We take 6 minus 6 equals 0. So there's no formal charge in that oxygen. And we could say the same thing for this one. This one's also going to be 6 minus 6 is equal to 0. And we can look at the carbon. Carbon has a valence of 4. There's 4 electrons in that middle red circle. So it's 4 minus 4 is 0. Okay, let's do water. So water is H2O. So we draw the Lewis structure for water, put the lone pairs in, draw our circles. Oh, that circle doesn't really show what I wanted it to show. That's cut right down the middle of that bond. And then finally we have for our oxygen, we have 6 valence electrons minus, once again, we've got 1, 2, 3, 4, 6 electrons in there. So 6 minus 6 is equal to 0. So notice we've got a bunch of zeros. Of course, that adds up to 0. So the sum of the charges in each of these is 0. And that's important because the formal charges have to sum to the charge on the molecule. Okay, great. Let's do something a little more interesting that maybe has some formal charge to it. Okay, let's look at carbon monoxide. So carbon monoxide, we know carbon monoxide has a, oops, let's do carbon monoxide. So when you draw the Lewis structure for carbon monoxide, it's a little bit unusual in that you've got 1 lone pair instead of 2 on the oxygen, and you've got a lone pair on the carbon where you normally don't see lone pairs on carbon. It's very unusual. So CO is it's a very unusual molecule, okay, and that's because of that carbon-oxygen triple bond. Great. Anyway, so looking at this, let's calculate some formal charges. So doing this, draw our circles, draw a circle again, and we'll calculate the formal charges. So let's do the oxygen first. So we've got oxygen has a valence of 6, as it always does, and then we subtract the electrons inside the red circle. So we've got 1, 2, 3, 4, 5, right? Because each of those bonds is broken in half, so it's a single electron, so that's 3 there, and then the 2 from the lone pair. So 6 minus 5 is equal to plus 1. Well, we know the molecule is neutral, so it must be that the carbon has a formal charge too. Let's see if that's so. So carbon has a valence of 4, as it always does. We've got the 3 bonds broken in half with 1 electron on each bond going to the carbon. So that's 3. Then we've got 2 from the lone pair, so we're going to subtract 5, just like we did with the oxygen. So 4 minus 5 is equal to minus 1. So notice, on carbon monoxide, we have a formal charge of minus 1 on carbon and plus 1 on oxygen, so it sums to be 0. So once again, the charge, all those formal charges have to sum to be the overall charge on the molecule, because this molecule is, after all, a neutral molecule. Okay, great. Now let's do one that's not. Let's pick a molecule that is charged. Okay, so we need some sort of ion. Why don't we pick the, well, we could pick the hydroxide ion. So first, let's write the formula for the hydroxide ion. And let's draw the structure with all the lone pairs. So when we write out the Lewis structure for hydroxide, we get that. Remember that we have to put an extra electron in. We've got the 6 from the oxygen and the 1 from the hydrogen, but we have to put an extra electron in because it's a minus 1 ion. Great, we draw our circles. And the hydrogen, it's pretty easy. We've got a valence of 1. We subtract the 1 from the half a bond, and that equals 0. And the oxygen, a valence of 6 as usual, but this time we've got 6 electrons from the lone pairs plus an extra electron from that half a bond, so it's 6 minus 7 is equal to minus 1. So that adds up to minus 1. And so, of course, all the individual formal charges have to add up to the charge molecule, or in this case over here we have a molecular ion. Okay, so this is a great way to test yourself, because you can take any kind of polyatomic ion, draw the Lewis structure, do the formal charges on the individual bits of that polyatomic ion, and then add it up to make sure that it adds up to the charge on the overall ion. And if it doesn't add up, that must mean there's either a mistake on your formal charges or there's some flaw in your Lewis structure.